and I'm going to share my document camera here. So okay, so we are doing the moment generating function technique, and we will continue that one. Huh? No? For the last handout, I haven't uploaded another handout. This handout is all for the whole complete chapter. What is the handout? 9? You can check that one. Huh?
I think so, but I can't find it.
You cannot find it on Canvas. There should be. Maybe it went to down because it was posted long before. This is handout 8. Handout 8. Did you get it? Yes? Okay. And yeah, we are starting the moment generating function, right? Moment generating function. So we are using the moment generating function technique for the transformation, finding the transformation. Now we let briefly start and review, okay? Review. So moment generating function theorem here, okay? Moment generating function theorem. Okay. So one theorem is that m x plus a and t. So it is a x plus a is a new random variable, right? Yes. So x plus a is, it means that it is a change of the origin, right? You add a constant number to the random variable. So this is equals to e a t m x, right? It means that if you know the moment generating function of the random variable x, then you can find if there is a change of origin for the another change of origin for the random variable. So you can find the moment generating function for changing. Okay. Now another is m. Now if you change the scale, okay, mxt, it means that the scale is changed. You multiply by some constant number, right? Constant number. So if you do that one, it is equals to m, x, a, and t. You see? Now if you know the moment generating function for the random variable x, you can also find the change of scale random variable. Okay, change of scale random variable. Now another one we did is that moment generating function can uniquely determine the density function, right? Moment generating function can uniquely determine the density function. So if moment generating function of random variable x, right? Moment generating function of random variable x, this is equals to moment generating function for another random variable y. So this is the random variable x, right? And this is the random variable y. If these two moment generating functions are equal for all t, if they are equal for all t, then x and y have same distribution. Same distribution. Okay. So if moment generating function are equal, then their density function is also same. And this is the theorem we will be using if we have the new random variable and we want to find the what is its distribution. Okay, what is its distribution? Okay. Now we did up to this last time, and we'll go continue. Okay, we'll continue. Yeah, this is the theorem we are talking here. Now the steps, how you do the steps. Okay, how you do the steps using the moment generating function. Okay, moment generating function method step. Let u be the function of the random variable y1, y2, and yn. Okay, so u is a new random variable, and y1, y2, yn. These are the random variable that we know their density function and their moment generating function. And u is a function of those random variables. So we want to find what is the distribution of this random variable u. We want to find density function of u equals to what, right? And u is a function of random variable y, right? And how we do that one? Find the moment generating function of fu for u. You want to find the moment generating function of u, and we already know the moment generating function of y. Okay, that is you want to find m u t. Okay, let me remind you here. This book is using the small m for the moment generating function, and I have used a capital M here, right? Capital M here. So just do not get confused, okay? Because I use sometimes capital M and it comes sometimes small m. The book is using the small m here. Okay, so it is the same thing. Just remember, it is the same thing because it is a small m here, and where you see I put here the capital M here. Okay, they are the same thing. Okay, same thing. Now you have the moment generating function of u, right? You have the moment generating function of u, and what you do is now once you find the moment generating function of u, you compare the moment generating function of u to the standard one, just like the binomial distribution, normal distribution, gamma distribution, those kind of thing. Okay, exponential distribution, whichever you know the moment generating function, then compare with those moment generating function. If the moment generating function are equal, if the moment generating function of the two random variables are equal, then you can recognize that what is the distribution of the new random variable u. You understand? So the idea here is now you have the function of y, that is a u, and you find the moment generating function for this u and compare this moment generating function with some standard distribution, non-distribution, and then you will know that what is the distribution of the new random variable u. You get it? Okay, that's what it is. So this is the step. So this is the steps you will be doing for this density function. Okay, now let's go ahead. Okay, so this was placed in misplaced here, so I'm going to cut this one here. Okay, now here you see here example here. Now y is distributed normally with mean mu and sigma square. Using the moment generating function, find the distribution of a and y. So u is the function of y here, right? So u is a function of y. And what is done here? It is scale here, right? Multiply by some constant a. Now, if y is multiplied by some constant, scaled by some a, now you want to find what is the distribution it will be, what it will happen. That's what we want to find, right? So now let me do it here. Now MUT equals to expected value of ETU, right? ETU, right? And this is equals, you can also separate as ET and U equal to A and U here, right? A and U. And now U is a random variable, right? This one U, this U is a random variable, new random variable, right? New random variable. U is a new random variable. That's what we want to find the moment generating function for U, right? So now you separate this mu U according to the definition of the moment generating function. Moment generating function of U and A and T is here now, right? Now in place of T, it comes A and T here, right? Now so this is equals to PU. This should be AY here. It's something wrong here. U equals to AY. 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 Not a U here, right? U equals to AY. U equals to AY. Right? U equals to AY. So this is equals to then Y here. Y here. Right? Yes? Y. Now this Y equals to this MYT equals to, this is the normal density function here. So this is the, we know this moment generating function of normal. So this is the moment generating function of normal. Moment generating function of normal distribution. Normal distribution, right? Okay. Now, in place of T, you have to replace by 80 now, right? So this is M mu, so mu 80 here because it is 80 now, right? In place of T, you replace by 80 here, right? Plus 1 over 2 sigma square, you put the sigma square in place of T, you replace by 80 and square here, right? 80 square. Now what you have to write is now this is a kind of, now you can recognize that, okay, this is the same as a moment generating function for the normal distribution, but with a different parameter value, right? So you organize as a E, A and mu to the one place so that the mean is now different here, right? In place of mu, this is now A mu here. The mean is different here. Plus half sigma square A square. Now, in place of the sigma square, you have sigma square and A square T, right? So what happened here? So this part is now mean here, right? This is mean here. This is mean here. And this is now variance here, right? This is variance here. In you see here, in this one here, this is mean here, right? Mu equals to mean, and this sigma square, this is variance here, right? Yes, variance here. So the new random variable A and Y has a distribution of the, now you see this moment generating function is the same as the moment generating function of the normal distribution, right? Okay? This is a normal distribution moment generating function, right? So you can write this one as a moment generating function of normal distribution. Right? This is also the moment generating function of the normal distribution. So we can say that U has a normal distribution with mean A mu and variance A square sigma square. Okay. So what we did here, we find the moment generating function for the new random variable u, and we match this one to the standard distribution normal, right? Normal distribution, and they match, right? The only difference is the parameter value. So we found that, oh, this is also a normal distribution with a mean a mu and variance a square sigma square. Did you get this one? Yes? Yeah? Okay. Now, whole idea is what? You find the moment generating function from the new random variable u, and you will have the moment generating function for u. And you match that moment generating function with the non-distribution. If they match, right? If they match, and if they match, then it means that also belongs to that match distribution. And here it is a normal distribution. Okay. Now see another one here. Okay, this one. Now, suppose y is a normal distribution with mean mu and variance sigma square. So y has a distribution normal with mean mu and variance sigma square, right? Normal mu and variance sigma square. Now, so that this g, now g has a standard normal distribution with mean 0 and variance sigma square. Now, standard normal distribution. So, standard normal distribution, G has distributed normal with mean mu equals to 0 and sigma square equals to 1. That is a standard normal, right? That's what you would like to find. Now, what is u here? In this problem, what is u? What is u? Now look at here. In this problem here, right? U equals to ay, right? Ay here in this problem. Now in this problem, what is u here? Huh? Y. Now y is a given random variable. We need a function of y here. You see like this one here, right? So what is u here? Yes. Huh? What? No, y is a given random variable. We need a function of y. You see here. We need a function of y. So what is u here? Huh? Yeah, f of y. What is that? In this, it is already there. You just have to recognize which one is that. G. You see, this y is here. So there are some constant here, and it is a function of this y. So this is G is u here. Yeah. Right. So G is a function of y here. Right. Function of y. Now, what we are going to do here? We want to find the moment generating function of G, right? We want to find the moment generating function of G. Then what will we do? Then we will compare the moment generating function of G with some standard distributions that is known and check whether they match. Okay. Now let's find the moment generating function of G. First, find moment generating function of new random variable, new random variable G. Okay, G equals to y minus mu and sigma. Right. Now you would like to find mg. Okay. Let me tell you again. I'm writing the capital letter here, and the book is writing the small letter. Okay, do not confuse. Okay, it is the same thing. So this is equals to m. Now you can replace g as y minus mu sigma and right. Now this sigma is a some constant number, right? Some constant number. Then you can apply the theorem here, m y minus mu t over sigma. Since m ay t equals to m y at, right? Using the formula, using the theorem we did last time, right? Yes. This theorem here, this one, right? This is one. Now we have y and some change of this is origin now, right? Change of this origin. Now apply this theorem here. You see this change of the origin here, right? X plus some change of the origin, right? You add or subtract some number, right? So it is equals to EAT So this is equals to my. Okay, I have to put here. This is equals to E minus mu t over sigma my since my plus a t equals to E a t my. Yes, do you understand this one? Right? Yes, Amanda?
Yes, that makes sense.
Okay, Amanda? Now in place of a here, we have the negative mu, right? So negative mu times this t is quantity is this whole quantity here, right? And my t is this t is the whole quantity here, right? Now we know the moment generating function for the y, right? We know moment generating function y. So this is equals to E minus mu t sigma, right? This now moment generating function y is distributed normal, right? Now we know the moment generating function normal, so that is equals to E mu t over sigma plus 1 over 2 sigma square t over sigma whole square. Yes, this is now moment generating function for the normal, right? Since y distributed normal with mu and sigma square, right? Normal sigma square. Now you have this one and this one, right? Now you can this is exponent, so you can add this one here, each power minus mu t over sigma plus mu t over sigma plus 1 over 2 sigma square t square sigma square. Now this is negative here, this is positive, so you can cancel this one and this one, right? Yes. And this sigma square, you can cancel this one here, right? So this is equals to E 1 over 2 t square, right? Now you see this one here. Now this is a moment generating function for m, g, and t. That's what we would like to find, right? Now we found the moment generating function for this random variable t. Now we would like to match this moment generating function with some standard distribution. Now we would like to match this one equals to, now if we see closely this one, this is same as a normal distribution with mean 0 and variance 1. How that one we can write in the form of normal. E 0t plus 1 over 2 1 square sigma square. They are same, right? 0t, it is 0, and 1 square sigma square, which is moment generating function of normal with mean what? Mean what? What is the mean here now? 0, right? This is the mean, mu t, mean 0. And what is the variance? This 1 square, right? This is t. I have to write t here. Variance 1. Okay, that's what this one is. Hey, did you get that one?
Yes,
Yes.
yes.
So that's what we would find the moment generating function for the new random variable using the moment generating function technique. Okay. Now let's do this one problem here. Okay. If y1, y2, and y3 be independent random variable with moment generating function my1t, my2t, and myn_t respectively. Now new random variable is u here, right? So u is the function of random variable y, right? Random variable y, and y are the independent here. Okay, these are independent here. That is the required. Okay, independent. Then you can find the moment generating function of new random variable, right? This u is a new random variable, right? As a multiplication of the random moment generating function for y1, moment generating function for y2, and moment generating function of yn. So if we know the moment generating function for y1, y2, and yn, then we can find the moment generating function for new random variable u, which is a function of y. Okay. Now this is a very useful formula, and we will be using all of this one here. Okay. Now let's prove this one here. Now u equals to function of y, so this is equals to y1 plus y2 plus yn, right? So it is a new random variable. New random variable. So we want to find now what is the density for u, right? U. So we want to just prove this one here in this problem. Now moment generating function, okay, I'm kind of writing the capital, okay, mut, we want to find this mut, and by definition this is equals to expected value of u t, right? Now this is equals to expected value of e. Now u is y1 plus y2 plus yn and t, right? Now you can multiply here. This is equals to e exponent y1t plus y2t plus ynt, right? Now, since this is exponent, right? Exponent, so you can write it as e y1t, e y2t, and e ynT. They are exponents, so you can separate one term, right? Each term, yes, because they are exponent, right? Now, y1, y2, and yn are independent, right? Independent. So if they are independent, then you can write this one as a e y1t times e y2t e ynt. Okay, because they are independent, we can write like this one here. Now, y1, y2, and y2, they are independent. So this is the moment generating function for y1, moment generating function for y2, moment generating function for yn, right? So this is the moment generating function of y1, right? Moment generating function of y2, moment generating function of yn, right? So this is equals to m y1 t times m y2 t times m yn. Okay, so m u t. Okay, so you can write moment generating function as their product. Now, this is the example here. Do you remember the moment generating function for the exponential distribution? Do you remember exponential distribution? Can you flip your pages? What is the moment generating function for exponential distribution? Okay, Autumn, what is the moment generating function for exponential distribution?
Isn't it in parentheses 1 minus beta t, and then all to the power of is it -1?
Yes. Huh? Did you get that one?
Yeah.
Okay. Now, what is the moment generating function for gamma distribution?
It's the same thing, but instead of to the power of -1, it's to the power of is it alpha?
Yes.
Okay.
Great. Okay. All of you guys understand that one, right? Okay. Now, because we are doing with the moment generating function technique here, so we have to know what is the moment generating function for some standard distribution: binomial, Bernoulli, Poisson, normal, gamma, exponential, those kind of things. Okay, we will need to understand by heart. Now, in this problem here, okay, the number of customers arrived at a checkout counter in a given interval of time possesses approximately a Poisson probability distribution. If y1 denotes the time until the first arrival, so y1, okay, the first random variable y1 here, and the y2 denotes the time between the first and second arrival. So time of arrival for the first person, and if it happened, one come, and the y2 is the time of arrival for the next second person, right? And if it happened, then the time of arrival for the third person, that's it is like that one. Okay, so yn denotes the time between the n-1 and the nth arrival. Okay, then it can be shown that y1, y2, and yn are independent random variable with the density function yi given by this density function. Now, can you recognize this density function now? What is this density function? Can you recognize this density function? We have done that one a lot. Yeah, which distribution is that? It is a distribution we have done a lot in maybe in a previous chapter. Can you flip the distribution and match which distribution? Huh? What? Can you flip the pages that which distribution it is? Okay, Autumn, Tiana, what distribution it belongs to? Look at this.
Is it exponential?
What?
Is it exponential distribution?
Exponential distribution. Okay, can you flip what is that one? Can you find in the note copy? Okay, Tiana,
Like,
there?
Are you saying find the equation?
Yes,
for
I'm here.
Okay, did you find what distribution this is? Looking at the density function,
Is it exponential?
exponential. Did you find the
Sorry,
exponential?
for the formula?
Yeah, it is exponential. Did you find that
Oh.
exponential? Okay, so okay, so remember the density function and the moment generating function for those 5, 6 standard distribution. Okay, it's required. It's required. Okay, since we are doing this. So this is the exponential distribution function, right? And it has a parameter theta here, right? Parameter theta here. Now we know what is the moment generating function for the exponential, right? We know that one. Okay. Now it says that independent here y1, here y2, and yn, right? And it has y1, y2, and yn are independent random variable here, right? So we have y1, y2 up to yn independent in the plane, then with exponent with exponent distribution, exponential distribution. Okay, exponential distribution. Now we would like to find the probability density function of the waiting time of from the opening of the counter until the end customer arrives. So we want to find the probability density function of the waiting time from the opening of the counter until the end customer. It means that the waiting time of the first customer, second customer, and end customer. So u equals to y1 plus y2 plus yn, right? So this is a function of the random variable y, and they are independent, right? They are independent. So we want to find the moment generating function of moment generating function of random variable random. So this random variable, new random variable u, right? Now you want to find the m u, right? So mut equals to m y1 plus y2 plus yn, right? Now, since they are independent, right? Waiting time of one person has nothing to do with the waiting time of the previous person and the coming person, right? They are independent. Now, independent they are independent. So you can multiply those moment generating function m y1t, m y2t, m y, right? Yes. Now y1, y2, and yn are exponential distribution, right? Yes. So we know the moment generating function for the exponential distribution. So this is equals to my1 equals to 1 minus, now here the beta is theta here, right? Theta t. Here. In this problem, we wrote the beta in our, whenever we did the exponential distribution, here they have written as a theta here, right? Yes, theta. So this is equals to 1 minus theta t, -1 here. And it has the same density moment generating function for this one, so you can write 1 minus theta t, -1. And this also has a exponential distribution, so this is also 1 minus theta t, -1. Right? Yes. Now they have the same bases, right? Yes, same base. So you can add 1 minus theta t, -1, -1, up to -1, right? How many times? N times, right? Yes, n times. So you can write this one as 1 minus theta t of minus n, right? So this is equals to, you can write 1 divided by 1 minus theta t power n. Now we found the moment generating function for the new random variable u. Now our task is to, we want to match this moment generating function with some non-distribution. Now what is that non-distribution? Now what is the moment generating function this belongs to? That's what we want to find. Remember, what is the moment generating, which distribution has this kind of moment generating function? This is the moment generating function for which distribution? Autumn, Tiana, do you know? Autumn told before, actually.
I actually don't know.
Is it normal distribution?
No, normal has a mu. Normal has
Exponential?
Is it binomial?
no,
Because
by
that's
not
that's-
by.
I don't know.
Is it gamma?
Yes, gamma. This is the moment generating function of gamma distribution.
I thought gamma was okay. Yeah, that makes
Gamma
sense. Never
distribution with
yeah, that makes
alpha equals to n and beta equals to theta. Right? Now we found
I have
that
a question. So how did you get, is it because since the -1, since it'd be negative, or sorry, is that because since n would technically be equal to the negative is it alpha?
yes, this will be alpha.
So that's why it's 1 over. So that'd be equivalent to, so that one right there, the 1 over 1 minus theta t to the power of n, that'd be equivalent to 1 minus theta t to the power of negative n.
You mean
right?
this one and this one?
Yeah. So that
They are
that
same.
whole thing, that whole thing would be equivalent to 1 minus theta t to the power of negative n, right?
Yes, that's what
Okay.
I just write it because we wrote in the very starting at in this form.
Okay.
Just they are the same thing, right? It is okay.
Yeah,
So,
that's where I got confused. Okay.
I have a question.
yes.
So for gamma, isn't the mean and the variance what is it, sigma? Or
For the
mean
gamma,
squared?
mean is what? Mean is alpha beta
Mean is alpha beta, and then the
and
variance
variance is
squared.
alpha. Mean is alpha beta and variance is alpha beta square, right?
Yeah.
Yeah. So now here we are matching the moment generating function. So we must know the moment generating function for that distribution. So you had a gamma with alpha equals to n and beta equals to theta. Okay, that's what it is. Okay, so what is the time? It's already time. Okay, now let's talk about now quiz. Okay, quiz. So Friday we will have a quiz. Friday we will have a quiz on the same thing, whichever we are doing. Okay, up to this point. So normal distribution, moment generating function for the normal distribution, and finding the matching those kind of problems, whichever we are doing today. So up to this point, we will have a quiz. Okay, on Friday.
Okay. I have a question.
Yes.
Will the format of the questions, because I know what we've been going over in class was kind of similar to the homework, but the homework was just more in depth. So would the quiz questions be formatted more so related to the homework or to the questions that we've been going on in the lecture?
Homework may have little bit depth because there is a linear combination little bit depth than this one. So we will cover up to this point.
Okay.
Up to this point. Okay. So homework has made a summation of AI and YI, those kind of a thing.
Yeah.
Yeah. So whatever we have done up to this point.
Okay. So should we expect questions that have like the AI and the YI and stuff like that? Or will it be like, because I know like the questions we went over in class or like the problems that we went over in the lectures are a little bit different. So will it be more based on the lecture notes that we've been going over up until now?
Most based on the lecture.
Okay.
But I may check that only using this knowledge. If you can do the assignment, whichever already assigned. So I may pick up from that one also. But what I'm saying is now in the assignment, there are little more complicated problem, or it means some other problems which we haven't covered and they will not show up. Okay. Hopefully that we can finish in the next class for this chapter.
Okay.
Okay.
Would you put practice problems on Canvas to prepare us for the quiz, or could we just look at the homework?
Yes, I will post the complete note in Canvas.
Okay.
Yes. Thank you. Okay. See you. Bye.
Thank you. Have a good one, Professor.
Thank you.